From this point on, you are going to learn how to use the equilibrium constant in different ways. First of all, we can make a qualitative description of the content of the reaction mixture by looking at the magnitude of Kc. Depending on Kc being very large or very small, we can claim that the reaction mixture contains mostly products or reactants. It's a qualitative analysis, qualitative description. Also, we can determine the direction in which a reaction will proceed in order to reach equilibrium. This starts with a non-equilibrium state, and the reaction will eventually reach equilibrium, but by favoring which direction? By favoring the product side or by favoring the reactant side. We're going to use the reaction quotient in that discussion. And lastly, we are going to learn how to determine equilibrium concentrations for any given initial set of concentrations and the value of Kc. Let's first talk about the qualitative interpretation of the equilibrium constant. Remember that the equilibrium constant is the ratio of product concentrations to reactant concentrations. So if Kc is a very large number, greater than 100, the equilibrium mixture contains mostly products. Products are favored. A large Kc means the numerator is much larger than the denominator. Since the numerator contains the products, that means there must be more products than reactants. Oppositely, when Kc is very small, less than 0.01, the equilibrium mixture is mostly reactants. Reactants are favored. If Kc is a small number, then the denominator must be much larger than the numerator. Denominator contains the reactants, therefore there are more reactants than products. When Kc is close to 1, the equilibrium mixture contains appreciable amounts of both reactants and products. Neither are favored. The ratio of products and reactants, numerator to denominator, is close to 1. Therefore, both products and reactants exist in appreciable quantities. Take a look at the complex ion formation reaction of silver and ammonia. The Kc value is 1.5 times 10 to positive 7. This is a very large value. It indicates that this reaction is product favored. We are going to see later on that large Kc corresponds to a negative free energy change, indicating that the reaction is spontaneous in the direction it's written. When you take a look at this example, the Kc value is 4.3 times 10 to negative 25. This is a very small value. Therefore, this reaction is reactant favored, and it corresponds to a positive free energy change, delta G. Therefore, you can consider this reaction to be non-spontaneous in the direction it is written. Let's talk about this reaction, which is the net ionic equation for most acid-base neutralization reactions. Hydrogen ions combine with hydroxide ions to produce water. The Kc value for this reaction is 1.0 times 10 to positive 14. This is a very large number, indicating that this reaction is product favored. Therefore, water is the predominant species. But what happens if you write this reaction in reverse? Does it change the fact that water is the predominant species? The answer is no. When you reverse a reaction, Kc value must be inverted. Therefore, the Kc value for the inverse reaction is equal to 1.0 times 10 to negative 14. A very small value of Kc indicates that the reactants are favored. That means water is still the predominant species. So what does all that mean? The reactions and the Kc values we are writing down are representations of real observations. You can write a reversible reaction in any direction you choose. That is your perspective. The main point is, perspective does not change the observations. From either perspective, water is the predominant species. You can represent an equilibrium system in any direction you want. You just have to make sure you use the correct Kc value.